Welcome to the Nautical Institute, the international body for maritime professionals. Helping our members to develop their knowledge and professionalism lies at the heart of what we do.
There's no doubt in my mind that my membership in the Nautical Institute has allowed me to grow as a mariner.
It helps you interact and network with other like-minded individuals all over the world.
Our industry is changing rapidly, and you are having to cope with new regulations, new technology, and evolving best practice.
You will actually have to link up or team up with a specific branch somewhere in the world, and they will give you feedback, their views. I think that just really adds to your professionalism, and it will basically be of great help.
Our website is the first port of call to learn more about us and the ways we can support you.
CPD Online is a programme that enables maritime professionals to keep current, to keep up to date. The whole programme is driven on templates that are downloadable from the website. So if you're at sea without internet access, you can download them and take them with you. They can be completed electronically or by hand. And all of the tools and guidance that you'll need to complete these templates and to follow the programme through are provided online.
The Institute is a superb vehicle for ensuring professionals are able to keep up with their professional development. How else can you stay at the cutting edge?
Another great advantage of membership is the Seaways magazine, which contains many articles, is published every month, and has a large amount of information for members on all kinds of shipping and nautical activities.
We have the ability to communicate with each other, voice concerns, put that either on the internet, on the website, or through Seaways.
The Institute produces a great range of publications, and as a member I receive 30% discount, which is just fantastic.
The Nautical Institute is about publishing best practice, and one of the ways that we do that is through our publications. They are written by seafarers or experts in their field for seafarers. So they're in seafarers' language. They're there to help you throughout your career as you rise through the ranks and perhaps as you come ashore and start a new discipline.
Go to our website at nautinst.org to find out more about the benefits of becoming a member. While you're there, explore the range of free resources, such as the reports submitted under our Mariners Alerting and Reporting Scheme. These confidential accounts of accidents and near misses are there to help us all stay safe, whether at sea or ashore. You'll also find out about the work we do to make our members' views known at key industry forums, including the UN's International Maritime Organization and IALA.
The Institute is at the forefront of making sure that the mariner's voice and the seafarer's voice is heard and given prominence.
I think it's really beneficial that the members' views are represented at key international forums such as the IMO, because it gives seafarers a voice.
Belonging to the Nautical Institute and Nautical Institute's philosophy of engaging with rather than disputing or debating, to constructively engage with similar bodies with a common aim of running a safe and efficient shipping. That has tremendous value to the sense of control that an individual member feels.
The Nautical Institute also offers accreditation services that support industry best practices. As a member of the Nautical Institute, you'll be entitled to use letters after your name, reflecting your professional status.
Having that experience, having those letters after my name, having the credibility of being a member of the Nautical Institute really helped me in my career.
It gave me an indication as an employer that the candidate was serious about the industry he was working in.
You'll also have access to a dedicated members area on our website that includes discounts on entry to leading industry events.
There is so much we can offer as a Nautical Institute. Our seminars, our conferences are absolutely top-notch.
I got the value of being a member of the Nautical Institute, particularly through networking. I needed to meet these people to advance my career.
Run by members for members, the Nautical Institute provides you with the ideal framework to support your professional role within the industry. Want to know more? Email us at member@nautinst.org or call us on 020 7928 1351. That's London, so dial country code 44 if calling from outside the UK. We'd love to hear from you.
We have a tendency, mariners do, to believe that our way, in our little part of the world, this must be the only way to do it. And of course, there's 1,000 ways to do it. And that broadening of our horizons, it's good for everybody. The Nautical Institute provides that platform.
It's a wonderful organization which has an outreach which is worldwide.
Without the Nautical Institute, I don't think I would be the mariner I am today.
As an international, independent and self-governing body, the Nautical Institute is here to serve you throughout your career as a maritime professional.
Good evening, everyone. Welcome to the Nautical Institute Sri Lankan Branch Youth Forum, the webinar on SQUAT. My name is Perera, and I will be the moderator for today. We have two speakers for the night. Captain Dhakshina Perera and Captain Harindra Perera. On SQUAT. My name is Perera, and I will be the moderator for today. A little bit on Captain Dhakshina. For the night. Welcome to the Captain Dhakshina Perera and Captain Harindra Perera. Captain Dhakshina holds a degree in law. He is a master mariner. He's the founder and general manager of MMA. He's a PNI surveyor, and he has several published research papers and one international patent. Captain Dhakshina holds a degree in law. He's a master mariner. He's the founder and general manager of MMA. He's a PNI surveyor, and he has several published research papers and one international patent. Captain Harindra Perera, on the other hand, is a product of St. Joseph's College, who started his sea career at the age of 17. In 1971, he was offered a 2-year scholarship by the Colombo Port Commission, where he was trained on board the Indian government ships. He's a product of St. Joseph's College, who started his sea career at the age of 17. In 1971, on completion, he joins the Ceylon Shipping Corporation, Lanka Kanti, as a cadet. In 1981, he joined Sri Lanka Port Authority as a pilot and was eventually appointed as the Deputy Harbour Master. Lanka Kanti as a cadet. In 2001, he moved to UK, where he worked as a pilot for very large vessels. In 1981, he joined Sri Lanka Port Authority as a pilot and was eventually appointed as the Deputy Harbour Master. In 2012, he came back to Sri Lanka and joined SINEC, where he is now the head of marine simulation and part of the research community. In summary, he has over 25 years of piloting and ship handling experience. He's a former PEC, pilot trainer and assessor for UK, Sri Lanka, and Malacca Max. He's auditor and has 8 research papers published and was the former chairman of the NISLB. Now I would like to introduce Captain Dhakshina to take the floor and to start on the webinar on SQUAT. For those of you who cannot access this webinar through Zoom, you can watch this on YouTube on the Sri Lanka Institute Nautical page. And also those of you who have questions, please send it through the chat, and whatever questions that comes to us, we will forward to the speakers today. If you have any technical difficulties, please send us a chat, so we will try to help.
Yeah. Thank you, Yashan. You all can hear me, right?
Yes, Captain.
Yeah, okay. Good evening. Can you all hear me?
Yes, Captain. Good evening.
Yeah, okay. Right. hope you all can see the screen. I'm taking my pen to the four corners. I hope you all can see my screen because I'm using the old school method. I'm not presenting any slides here, few slides only, but everything, whatever the explanation will be totally done here in this white paper. So if you cannot see the four corners and if you cannot see what I'm writing, please let me know. And whatever the questions that you have, you can pass on. Right, just I need a confirmation whether you can see the four corners. Is it? It's good, right? You can see my pen, right? Right, okay, so we'll start. Right, so let me straight away start from a question, right? I'm sorry that I may have to go a little bit fast in the explanation. That Scott is not just a single explanation. There are to explain Scott, there are certain hydrodynamical principles needs to be explained first. So we'll start from the beginning. So let me straight away start from a question. Now, if I draw a ship here, right? Let's say this is the water level, and there is certain underwater volume for this ship, right? And let's assume that the ship's displacement or the weight of the ship is, let's say 20,000 tons, right? So this is a small stability question, right? So the now ship is floating in water with a certain underwater volume, and this is a cross section of the ship, right? And now a slight wind is coming from this side, a slight wind or some external force is coming. So after a while, the ship is going to heel into one side. Right, the ship is going to heel into one side, but the weight is same, 20,000 tons, right? And the underwater volume is changing. You can see the shape of the underwater volume is changing. So the question here is that the underwater volume here at this location, at this point, and the underwater volume at this point, are these two underwater volumes are same? So that is a question. So if anybody can answer the question, you can put it on the chat. I hope you can see the chat, right? You can see the chat. Right, so please just put the answer. So the question back again. The ship is floating in calm sea, right? And the weight of the ship is 20,000 tons. There is a slight wind is coming. Now the wind is gone. But at this location, when the ship is here, it will get corrected after a while, yes. But at this moment, right, the weight of the ship is same, but the underwater volume. My question is the underwater volume is same at this location and at this location, at this condition and at this condition? Are these two underwater volumes are same or different? So basically, for a ship to float, right, the ship is having a weight acting downwards and upthrust is acting upwards, right? So these upthrust and the weight according to the stable condition of the ship needs to be same. If one is more, that means either ship has to go up. If weight is more, the ship has to go down, right? So the upthrust always equals to the weight of the ship. So the question here is the upthrust is changing at these two conditions? Can it change in the first place? Now, as the weight is not changing of the ship, the weight is constant. So in that case, upthrust cannot be changed. So basically, the weight is equals to upthrust. So upthrust is going to be the same value in the first condition as well as in the second condition. If the upthrust is same, then what about the underwater volume? So according to the Archimedes law, underwater volume is the function which emits the upthrust. So underwater volume is going to be same if the upthrust is not changing. Right? I hope you all can understand. Unfortunately, the interaction is not cannot be taken as in a class. So I hope if there is something, please put it into the chat so that I can see some confirmation on the questions. Okay. Now let me explain back again. The weight is not changing, right? The upthrust is there. As the weight is not changing, upthrust cannot be changed. That means if the upthrust is not changing, the underwater volume cannot be changed. Now, even in a wave condition, when a ship is moving, right, the weight is acting downwards. But what about the underwater volume? Right? The upthrust, if the ship is in a stable condition, upthrust should be always same, which will be equal to the weight of the ship. So if the upthrust is not changing, what about the underwater volume? Can it change? With the wavy condition, the underwater volume is changing, yes. So that means when the underwater volume is changing, the upthrust is also changing, but the ship will act accordingly. Maybe the ship will go down to achieve the required upthrust, or maybe the ship will come up to achieve the required upthrust. Right? So underwater volume will ship automatically adjust the underwater volume to achieve the required upthrust, right? So that is why the motion is coming to the ship. That is where the motion is starting. The ship is going up or down. Heaving motion will be commencing at this point. So my question is now, as you all know, I'm sure this is a bit of a technical presentation, so I assume that you have certain understanding on terminology, right? So now the next question: if the ship's weight is not changing, that means the upthrust is not changing, right? So underwater volume cannot be changed. Underwater volume, basically, it cannot change. Now, when it comes to Scott is when the ship is moving, right? When the ship is moving, a bodily sinkage is there. The body of the ship is sinking. That means if you take the draft here and if you take the draft here, the draft is going to change. The bodily sinkage is there. So when the draft is changing, as you all can see, the underwater volume is also changing. If the underwater volume is changing, then the upthrust changes according to Archimedes' law. Unfortunately, I cannot explain Archimedes' law at this point because this webinar is about, we have limited time here, right? So unfortunately, I cannot explain that in detail. But anyway, I hope you all understand that underwater volume is increasing if it is, during Scott. Right? If the underwater volume is increasing, the thrust is also changing. Then what about the weight of the ship? Weight is same. So can this happen in the first place? That means, can the underwater volume change if the upthrust is, if the weight of the ship is not changing, and the underwater volume will be same according to the upthrust? So can this happen in the first place? Can the draft increase during Scott? So I hope all you can understand my question, right? So if the draft is increasing, underwater volume is changing. So if the underwater volume is changing, the upthrust is changing. If the upthrust is changing, then if it is more than the weight, the ship should go up instead of going down, right? So can it happen in the first place? So, but we all know that during Scott, the bodily sinkage is there. It's a natural phenomenon that it is happening. So then what is happening? So then what exactly happening? Is the underwater volume is changing or not? We all know that the draft is changing. So that means definitely there is a change in the underwater volume assay. To explain this, right? To explain this, I have to start from the pressure systems. So let's go to the pressure, a little bit of hydrodynamics. I'm sorry, I will be using a little bit of mathematics here. I will try to simplify as much as possible the mathematics part. areas of mathematics. I will try to simplify as much as possible, but to explain these areas, I have to use mathematics a little bit. So now, I hope all you can hear me, right? Right. So let's come to pressure first, right? When it comes to pressure, there are two types of pressures. Number one is hydrostatic pressure, and there is something called hydrodynamic pressure. So what is static pressure is that if you take a liquid, this liquid is having, I mean, let's say this is a kind of a chamber where you have a liquid, right? And if you have a liquid, this liquid is having these two types of pressures, right? But if you, when we define the pressure, pressure is defined as the force. Pressure is defined as force acting in a unit area. It is always a force. So the definition of pressure is force acting in a unit area. Now that means if you have a force, you have a pressure. If you have a pressure, you have a force. So what is a force here now? What is this hydrostatic pressure or the hydrostatic force? Right? If you take all these particles, for example, these water particles, each and every water particle is having a weight. This weight is acting downwards, and when this weight is acting downwards and all this weight accumulated together, if you take one plane here, the weight is acting on this plane. All these water molecule weights are acting on this plane. As the height is changing, this weight is also changing. You can, I mean, all of you can understand that. I will give you another explanation. Now, if you take this circus people, right? You take circus people. If you, I mean, these people are climbing on top of each other. Let's say this person is having 50 kilograms weight, and this is also 50 kg. This guy is also 50. So the weight acting or the force acting on this guy is the bottom circus guy is the legs are 150 kilograms. So this is the weight acting on this guy's feet. Now, if you take the atmospheric pressure, for example, in the atmosphere, the same thing is happening. The atmospheric pressure, now, as I explained earlier, pressure is a force. So what is the atmospheric force now acting? If you take atmosphere is extending for about 200 kilometers, right? Where each and every air particle is having a weight. So all these weights, like these circus guys, all these weights are accumulated together and acting on the surface. So this is atmospheric pressure. Now this is a static pressure. This is always there, right? Why it is called static? It is a static. The opposite word of static is dynamic. So this is whether it is moving or not. This is there. That means each and every particle is having a weight, and all these particles, the weight is getting accumulated and acting on a plane, right? So that is static pressure, which is given by H rho G. Right, I'm just putting the formulas just for the explanation purpose only. Even if you do not understand, that's fine. Right. Now, this is static pressure, and it is a force. Now, if I open up a tap here, this water will flow out. And if I keep my hand here, what will happen? You can feel the force, isn't it? So this force is a function of the movement of the water. Right? So that force is called the dynamic pressure. So when you take a liquid, there are two types of pressures, static pressure and the dynamic pressure. The same thing when the ship is moving. Right? The same scenario is happening when the ship is moving forward. So I'm going to explain this pressure systems by using the eductor system on board a ship. Right? Otherwise, it will be a bit difficult to explain without the pressure systems, the Scott effect, right? So that is why I'm explaining from the beginning. So I'm going to draw an eductor system, right? I hope that you all have a bit of a technical knowledge. What the eductor system is, it's like a pipeline, right? Where the pipeline is getting thin. Right, there is a reducing pipeline. This is a reducing pipeline where another pipe is coming and going into a ballast tank. Okay, and the ballast tank is having a vent. So now what in the eductor system, what is happening is that right? When the water is flowing through this pipe, it gets squeezed in and moving faster at this point. You know, if you have a pipeline, right? Let's say you take a rubber pipe and you squeeze the end, what will happen? The velocity will be increasing. You can see that. That is why this is getting reduced here, right? Velocity of the water is increasing at this point, right? So now, there was a scientist called Bernoulli. He said that at any given point, in this flow, if you add the hydrostatic pressure and the hydrodynamic pressure, it will be equal to a constant, right? So if you take this place or in this place, right, if you add hydrostatic pressure and the hydrodynamic pressure, it will equal to the same constant, right? But that does not mean the constant means now this was derived by the conservation of energy. So the energy is not getting assuming that there is zero resistance in the pipe, right? So that is why the energy is getting a constant value in this point and at this point. So anyway, assuming that there is no any resistance in the pipe, right? So the Bernoulli said that if you add the hydrostatic pressure and the hydrodynamic pressure at this point will be equal to a constant, and even at this point, if you add these two, it will be equal to a constant. But that does not mean the hydrostatic pressure here and the hydrostatic pressure here should be same. For example, let's say this constant is 100, this should be also be 100. But that does not mean that this is 50, this is 50. It doesn't need to be. Let's say this is 60 and this is 40, right? This will can be another value. For example, it could be 40 plus 60. But finally, both accumulated together will give you 100. That is what Bernoulli said. So now let's look at what will happen to I will be using a little bit of formulas here now, right? I will be focusing on this hydrodynamic pressure. So hydrodynamic pressure has something to do with kinetic energy. So kinetic energy, maybe if you are familiar with physics, you know that the kinetic energy will be given by this formula, half mv squared, right? Half into the mass and the velocity of an object. So this is for object. When you throw an object, for example, let's say you are throwing a ball and the ball is having a kinetic energy of this much, mass into velocity squared. But when you take a liquid, you cannot give a mass for the liquid. It is a bit difficult to give a mass for the liquid, but you can give, let's say in a pipeline, you can give mass for unit volume. That means you can take a unit volume of a liquid and you can give the kinetic energy for this unit volume, right? So when you give a kinetic energy for a unit, that means mass divided by the volume, right? When you give a mass for a unit volume, this is a unit volume and it has a certain mass depending on the density of that liquid. So that is the kinetic energy of this small piece of the liquid, right? So if you think from that point of view, so the mass per unit volume is given as, so mass divided by volume is basically the density of that liquid, which is half rho v squared, right? So when it comes to a liquid, the kinetic energy can be given as half density of that liquid into the velocity squared, right? So this is going to be basically representing the hydrodynamic pressure, right? Now I will draw the hydrodynamic pressure here. Let's say there is this, at this point the velocity of the liquid is v1, at this point the velocity of the liquid is v2, right? So if I draw the hydrodynamic pressure here, if I show the hydrodynamic pressure, it is going to be half rho v1 squared. Here it is going to be half rho v2 squared at this point. So here half rho v1 squared, here half rho v2 squared, right? Now, what will happen is that you can see here the velocity is increasing because of this reduction of the pipe diameter. The pipe diameter is getting reduced and the velocity will be increasing. So what will happen? V1 is the velocity here, but V2 is more than V1. So what happened here, when V2 is more than V1, the hydrodynamic pressure here increases compared to here, because V1 and V2, V2 is more compared to V1, but to maintain the same constant, the dynamic pressure is going up. When the dynamic pressure, I will draw it here, HS1 equals plus HD1 equals to HS2 plus HD2, because the constant is same according to the Bernoulli's theory. Now, when HD1 is going up here, sorry, my mistake. HD1 is going up here comparatively. Okay, so when the HD1 is going up, to maintain the same constant, what will happen to the HS2? What will happen to HS2? To maintain the same constant, when this is going up, right? To maintain the same constant according to the Bernoulli's theory, this has to go down. So that means the pressure is dropping here. At this point, the pressure is dropping. What pressure is dropping? The hydrostatic pressure is dropping, right? So when hydrostatic pressure is dropping, the tank inside is having water. This is a ballast tank, right? And you can see atmospheric pressure is acting through the vent and acting on the water surface. This is atmospheric pressure, right? So your vent should be very in good condition. Otherwise, the atmospheric pressure will not be coming in, right? So this is acting on the water surface, right? Now, if your pressure drops here, less than the atmospheric pressure, if the pressure drops here, that means the static pressure drops here less than the atmospheric pressure, what will happen? The water will be going up. So this is basically the ductor system. And you don't have to prime this system because there is no any priming requirement. It's basically if that pressure here drops, that means you have to increase the velocity of the water in such a way that the static pressure should drop less than the atmospheric pressure, and your vent should be in very good condition. If the vents are in bad condition, atmospheric pressure will not come in, right? And the water will not go up. So that is why the vent should be maintained and vent should be in open condition. And sometimes if something happens, if the vent is closed, what will happen? The tank will get squeezed in, right? Right. So this is the Bernoulli theory. But why I explain the Bernoulli theory is just to explain a very simple phenomena. That means if the velocity of the liquid goes up, pressure drops. So that is a conclusion we can come into from the Bernoulli's theory and the ductor system, that if the pressure increases, the velocity increases of the water, hydrostatic pressure is dropping. So that is the first conclusion. So I will draw the first conclusion here. Velocity increases, pressure drops. That is the first conclusion. The second conclusion is that you can see it is squared, right? So when you change the velocity by a small amount, the pressure is dropping. You can see this is a squared amount, right? It increases by squared amount. The pressure is dropping or changing by a very big amount, right? So that means if the ship's speed, if you drop the ship speed by a small amount, speed of the ship, the pressure system around the ship is changing by a huge amount because of this. So there are two conclusions. Velocity increases, pressure drops. Velocity changed by a small amount, the pressure is changing by a larger amount. So that is the second conclusion. So now, I think if you have any questions, you can shoot the questions before I go to the next section. I will hand over to Captain Harin. You can ask any questions, more practical questions.
Thank you, Captain Dhakshina. We have a question from Dinuka Piris. This question is addressed towards Captain Harindra. Usually ships are maintaining trim towards aft. Suppose if you are coming to port and you have a forward trim, as a pilot, what additional precautions would you take in comparison to a vessel with an aft trim?
Yes, thank you very much for that question. And first of all, thank you very much for inviting me to be part of this forum. Yes, most of the time, either we arrive in port on even keel or trimmed by the stern. So there are times when the ship, especially at times, I remember there was an incident and we were, many ships are doing a lot of slow steaming these days, or even the early days. And to get the maximum efficiency on the fuel consumption, the ship used to be trimmed by the head, maybe 1 meter, or container ships and with slow steaming to for economical purposes. So there was this ship which arrived in the port, came to pilot boarding position, and the pilot got on board. And later on, it came to know, the pilot just, it was related to me. The pilot asked what the maximum draft was. So maximum draft was 13 meters, and we come into port with 1 meter under keel clearance. That is to Colombo sometimes the maximum we are allowed to come with, but maybe some the ship's SMS says maybe 10% UKC requirement, but so there's a lot of very minimal Scott, very minimum UKC. So when he got on board and brought the ship in, he thought it was coming into port, found it very difficult to, this ship had come to port before, and this pilot as well. So once it came into the harbor, went to stop the ship was a problem, and felt that there was something wrong in trying to the stopping distance. And ultimately, what happened was the mate had not corrected the trim, the head trim, and the ship it took a lot of distance to stop the ship, and letting go anchors as well in order to not hit any other jetties as well. So that was yes. So so again, a little bit more. What about Scott? Scott is the bodily linkage. Now, Scott depends on your type of ship, whether in addition to your bodily linkage, you will go down by your head, or by the stern. Now, what determines whether the ship is going to go down by the head or by the stern in way of Scott? Now, you can go to your, if you can remember your last ship, when you go to your ship and see this in your maneuvering diagram, you will find the Scott tables, right? And then you will find whether in Scott tables are given for shallow water and also for deep water. So the Scott is more in shallow water. And you will find, depending on the type of ship, whether it's a bulk carrier, whether it's a container ship or it's a passenger ship, so it all depends whether you're going to trim by the head or trim by the stern, if you're on an even keel, and then your Scott tables as well. And that is dependent on the block coefficient. So you have to be careful on which way you're going to Scott. And I had an incident where I had to board a Malacca Max VLOC. I boarded off Gaul and got off in Singapore, and it was maximum draft for the Malacca Straits, where the draft was 20.5 meters, and I had to assist the master, and we had a very good passage plan in order to have 2.5 meters under keel clearance. And what did we do? We had to slow down to 6 knots to make sure that she was cutting only 1 meter. And we did trim the ship by the stern, because this was a bulk carrier. The Scott, she was going to Scott by the head. So, and also we had to slow down for the high water time to pass the shallowest area, which is near the 1 fathom bank where you call the goalpost. The goalposts are there, so that was the shallowest area. And that was quite a challenging exercise to go through that. Yes. So there are times when ships come through. The Scott is greater in a narrow channel and the blockade factor, and rather than in deep sea, as you can see when you go to your Scott tables in shallow water and deep water. And again, signs of Scott, you know, how will you, you will have a difficulty in steering your ship. And also maybe you will have some vibrations, and also maybe your revs will come down, engine RPM. So these are also signs for you to watch out and act accordingly to reduce the Scott. Yes. Thank you.
Thank you, Captain Harindra. Now we'll go back to Captain Dhakshina. He will continue the rest of the lecture. Captain Dhakshina, the floor is yours.
Yeah, okay. Thanks. Thank you, Captain Harindra. All you can hear me, right? Okay, right. So let me come back to the topic back again a little bit. Again, this is a reminder that the velocity, according to the Bernoulli theory, if you change the velocity of a liquid, the pressure is dropping if you increase the velocity. And if you change the velocity by a small amount, the pressure is dropping by a larger amount, which we have seen by the formulas. So now, how this is going to affect the Scott phenomena without changing the underwater volume. Now the ship has to go down. According to the Archimedes law, underwater volume cannot be changed as well. The ship will be going down. At the same time, underwater volume cannot change as well. So then how this is happening? So the draft is increasing, but the underwater volume cannot be changed. Okay. Then there is a conflicting situation with Archimedes law and the real actual phenomena. So now how this is happening? So let's see. I hope you all see the previous inductor explanation. Why I use the inductor is it is easy to explain the Bernoulli theory. That is why I use the inductor system. So finally, what you have to remember is that the pressure system around the ship, right? Where you have high pressure system in forward, high pressure system in aft, and low pressure. But unfortunately, I cannot explain in detail why this is happening. But this can be explained by using the Bernoulli theory. But how this is happening will be a bit difficult to explain within the time constraint. If you need furthermore explanation, it is I have my YouTube channel where deep explanation with the mathematics are there. You can visit and you can have a look. But anyway, now if you look at this situation where high pressure system is forward, high pressure system is aft, low pressure is in the side. Now this is not dynamic pressure, this is static pressures, right? This is static pressure. And here the low pressure is, don't get confused. Here the low pressure is, this is not lower than the outside. This is the comparatively, this pressure is low compared to the outside water. So this is comparatively higher, this is comparatively lower to the outside. Reference is the outside water pressures, right? So now when the ship is moving forward, right? When the ship is moving forward, let's say when I give a velocity to the ship, right? There will be a bodily sinkage. But the problem is when there is a bodily sinkage, the underwater volume is increasing. So according to Archimedes law, as I explained earlier, according to Archimedes law, underwater volume cannot be increased because the upthrust is changing if the underwater volume changes. So how the ship is going down at the same time without the change of the underwater volume? Now I have to come to another phenomena called resistant types for a ship. Now, if you take a ship, I'm sure you have heard of resistant types of a ship. If you take a ship, right? Normally in naval architecture, they consider there are about basic 6 types of resistance. Under the water level, there are 3 types of resistant types. At the water level, there are 2 types of resistant types, and above the water level, there is 1 type. For example, under the water level, there is something called separation drag, right? Then there is something called frictional drag. Then there is something called the viscous pressure drag under the water, right? I'm sorry, I cannot explain in detail here that part, the resistant types. So at the water level, there is 2 types of resistance that the ship is facing. One is wave making drag, and there is another one called wave breaking drag. So another one that above the water level, there is windage, right? So all these resistance have to be compensated by the engine. So basically there are 6, but there are more than that. Okay. So now out of these 3, there is one called frictional drag. This is called frictional drag, right? So let me explain what is frictional drag is. Right, this is called frictional drag. So when a ship is moving forward, right? When a ship is moving forward, we draw the ship like this. When a ship is moving forward, as you all know, that the wetted area or the hull where the water is getting compacted, the wetted area, we call the wetted area. Even though whatever the paint types, how much we have polished the hull, there is always a friction, right? There is always a friction in the hull, right? Even though how good is the paint is, still the friction is there. And also there are dents in the hull because the hull plates are compared to older ships, hull plates are now getting thinner, right? The reason is now the technology is very high, so the required thickness can be computed by softwares, what is the thickness required, and also the hull plates, the thickness varies from forward to aft. It does, for example, those days, I mean, several years back, the thickness of the hull plate is basically constant from forward to aft. But nowadays, it is not like that. According to the, if you take a cross section, according to the cross section, through a computer simulation, which is called computational fluid dynamics and finite element analysis. By using these 2 methods, they can find out what is the required strength for the hull at that point. So accordingly, the thickness of the hull will be decided, and accordingly, the plate will be decided. So likewise, the plate thickness is coming down. That means if you go to a dry dock, you can see that there are slight dents inside, right? Because of the pressure, right? So that is also a function of this frictional drag, not only the smoothness of the hull, but also the dents that you can see between 2 frames, right? Now what will happen when the ship is moving forward? Let's say the ship is doing 16 knots forward, right? The immediate water layer just next to the ship, the immediate water layer just next to the ship will also getting a velocity forward, right? This will also getting a velocity forward. It is not going to be 60 knots, but somewhere between 0 and 16, very close to 16. Let's say this is 15 knots, for example. Right. This water layer is also getting a motion because of the friction of the hull. And that is also moving forward. Right. This is calm sea, no wind, no current, nothing. It's all calm sea, but this layer is moving because of the ship friction. Right. Then the next layer, just next to this layer, because of the viscosity of the seawater, viscosity is the attachment of molecules to each other, viscosity of the seawater, the next layer will also get a movement forward, but that is not going to do 15 knots, something less than that. Right? So because of this layer, the next layer will also get a movement. So likewise, there will be from the ship's hull, up to a certain point, this water layer is getting a motion. And that is basically because of ship's hull friction. And as the age of the ship is increasing, this layer is also getting bigger and bigger. You can put the vessel into dry docks, but you cannot eliminate all this back to the present, the condition where the ship was built, right? So if you draw the graph, for example, with the edge of the ship, this friction, now this is the edge of the ship, and this is the friction of the ship, which is friction of the hull, right? So when the ship was built, it is very low, but it is not zero, it is very low, right? As the age is increasing, it will go up. You can put the vessel into dry docks, you can paint and do the hull painting and stuff, but it will come down, friction will come down, but it will never reach the previous condition. So likewise, as the age goes on, the friction will be increasing, right? So when the friction is increasing, the layer is also getting increased. When the layer is also getting increased, what will happen? This is called the boundary layer of the ship. This is called the boundary layer, right? This is called the boundary layer of the ship. So that means when the ship is having additional mass is added to the ship, that the engine has to work for this boundary layer as well. So this layer is basically a waste of energy for the engine, right? If the ship is having a mass, this boundary layer mass is called the virtual mass. The added mass of the ship. So the boundary layer is adding to the ship's engine, so that is called added mass. So the whole mass is called the virtual mass of the ship. That means virtual mass of the ship is equals to the ship's mass plus the added mass of the boundary layer, right? So the engine has to do work for that one as well. So that means this layer is moving with the ship basically, right? So this is like a basing which is moving with the ship, like the ship is in a kind of a chamber and the chamber is moving and the ship is on top of that, right? So what will happen during Scott, right? During Scott, so what will happen is that now the ship is there moving forward at a certain velocity, right? I will take a confined channel over the shallow water condition, right? Now what will happen when the ship is moving? This area, this underwater area have taken some area of the water volume, right? So when the ship is not there, this is totally water. But now when the ship is there, that water have been displaced out. So now when the ship is moving, relatively, this water is getting squeezed in, like in the ductor system, right? And if you can remember the ductor system, the reducer, the same thing is happening here, right? So what is happening here is that when this is getting squeezed in, the velocity of the water increases. So if you can remember the conclusions that we came earlier, when the velocity increases, the pressure is going to drop, right? That is, static pressure is dropping. So the pressure underneath the keel is getting dropped. So my next question, is it dropped from the keel itself or after the boundary layer? This is the boundary layer. Is it reducing after just next to the keel or just next to the boundary layer? So unfortunately, you cannot answer this question because this is not an interactive session. So now you all can see there is a boundary layer acting around the ship, right? The reason is the friction of the hull, right? So now the water level is getting squeezed, not underneath the keel actually, but underneath the boundary layer. So it is not the keel which is going to be the first contact of this water. It is the boundary layer is going to be the first contact of this water. So the pressure is dropping under the boundary layer. So when the pressure is dropping under the boundary layer, the whole ship is coming down, but with the preservance of the boundary layer. So when the boundary layer is coming down, the draft is not changing. You can all see that draft is preserved, but the whole boundary layer and the ship is coming down, like it is in a you put a big bucket or something and put the ship there, and the whole bucket is moving, right? And the whole bucket is moving. The bucket is getting the pressure drop, but the draft is preserved that the whole bucket is coming down. So you can consider that this boundary layer as a bucket, the whole ship is coming down, but the underwater volume is preserved. So that is why you will see a draft change because of the high pressure system here. You can see high pressure system here, and there is a crest here. There is a low pressure system. You will see a trough here, and there is a crest here. But that does not mean that the draft is increasing. Draft is actually, it is a virtual increment. That is why it is called virtual body linkage. So this is virtual only. It is a virtual increment in the body, but the whole system is coming down. So Archimedes law is preserved, underwater volume is not changing, but at the same time, the ship is coming down because of the boundary layer. So this is Scott, right? This is Scott. So again, I will hand over to Captain Harin for the questions, right? Yoshan?
Thank you, Captain Dhakshina. We have another question from Capt. He's asking that during a sea passage, vessels echo sounder may malfunction. So when they're going through a narrow channel and because of commercial pressures, the captain cannot say, no, we cannot go. They have booked the pilotage for high tide, but the pilot has come on board during the lowest possible tide. As a pilot, what precautions do you take? Captain Harindra, this question is for you.
Yes, thank you for the question. I think, yes, pilot boarded at high tide, and the berthing has to take place at the low water slack window. So that will take, you will be proceeding down the river, up the river at ebb tide. That will have the current ahead of you. So you have to be very careful in your Scott. I mean, most of the time we go to the limit, and maybe the draft is normally you need 10% of your draft at least minimum. But where we pilot, we in the UK or in Sri Lanka, we go down to about 1 meter UKC. So that is the, if you are going to the limit, you've got to be very, very watchful. And especially when you said the echo sounder is also not available. So we will stick to the port rules, and as well as to the company SMS, and the master always can say if he's unhappy to proceed. And we had this kind of thing when the spring tides turn into the neap tides. Spring tides turn into the neap tides, and I remember once where the master refused to proceed because he didn't have 10% UKC. And next day, the tide was going to be, the range of the tide was going to be less and less, and it was turning out to neap tides. And ultimately, the company refused, as the charterers, like you said, the commercial pressure comes in, the charterers were pressure come on. And finally, the ship could not be berthed, and she had to go to Rotterdam to do some lightering and then come back. So it was quite an expensive detour or rerouting to discharge, part discharge, and come back, and because she could not make it because of the tide. So the commercial pressure and the high, so you really have to watch out for any steering problems and vibrations and reduction of RPM and things like that when you are proceeding with minimum UKC. So yes. And also when I spoke to you last on that with the bow, vessel was trimmed by the bow, the first thing that you should do is to put a button, a tug right astern, so that your stopping distances and things are controlled, because you will take so much more distance to stop your ship. And also maybe in the allocation of tugs, maybe you'll put a more powerful tug on the bow because you are down by the head, and allocation of the tugs. You won't have all the tugs of the same power. So the bigger tug might have to be right astern, and the next one might be on the bow instead of the quarter. So yes, so I hope that I wanted to catch up on my last as well. Yes, thank you.
Thank you, Captain. Thank you for answering that question. Captain Dhakshina, will you take the floor again?
Yeah, okay, Yoshan, thanks. Captain Harindra, thank you. You all can hear me, right? Okay, so let me come back to the explanation back again, why the body linkage is there, right? So I showed you that previously the boundary layer. So the reduction, I mean the squeezing of the water is happening underneath the boundary layer. Because of that only the pressure is dropping underneath the boundary layer. So when the boundary layer is coming down, the whole ship is coming down, right, preserving the drafts, but you cannot see it because of the high pressure system. There is a trough, crest, and the trough, right? So right, so now I come to trim. Right, as Captain Harindra explained, I will explain it through hydrodynamics, why the vessel is getting trimmed, right? Because of Scott, right? Right, now, okay, again, another question, right? So now we'll go back to the previous question back again. I hope you all know the answer for this. Now you have a ship, right? This you have a certain underwater volume, right? The vessel weight is 20,000 tons. Okay, there is a certain underwater volume, right? And there is a side wind is coming from the side, and the ship is going to heel into one side. There will be a heeling, right? The weight is same 20,000 tons, okay, right? And the underwater volume is same as the previous, because if the underwater volume is changing, then according to the Archimedes law, it cannot happen, right? So that is why the underwater volume is preserved at any given time if the weight is not changing, right? Now my question is, in order to achieve the same underwater volume, where should the vessel should pivot? I hope you all know the answer if I give you some points here, right? If I give you the keel, G, B, metacenter, center of gravity, center of buoyancy, metacenter. Okay, keel, center of gravity, center of buoyancy, and the metacenter. Okay. Around what point that the vessel should pivot or turn to achieve the same underwater volume? If I ask you the question back again, now, for example, let's say if you pivot from center of gravity, keel, can you achieve the same underwater volume? If the vessel pivot from center of gravity, can you achieve the same underwater volume? Or if you rotate around center of buoyancy, can you achieve the same underwater volume? Or metacenter? So I'm sure you can put your answers here in the chat, right? So the requirement is underwater volume should be preserved. This is transverse section condition, and I will come to the longitudinal condition later. First, I will explain this transverse condition, and I'll come to the longitudinal condition. So this is transverse heeling of the vessel, right? So I hope you all understood my question. Around what point the vessel should heel so that the underwater volume will be preserved? So is it K, is it keel, or is it G, is it B, or is it M, or is it something else? Right? Anybody would like to answer that one in the chat? Right, okay. Okay, anyway, It is none of these basically. It is not the K, it is not G, it is not B, it is not M. It is basically this point, which is called the center of rotation. Why is the center of rotation? Why, if you pivot around the center of rotation, that the underwater volumes are getting preserved? Again, it is very simple. Look at the wedges around these two sides. This wedge is gained, this wedge is lost. But these two wedges are same. So the underwater volume is getting preserved. This is lost, this is gained, but since these two are same, underwater volume is preserved. But if you take another ship, for example, naval vessel like V-shaped ship, right? This is not going to happen like that because those two wedges are not be equal because of the shape of the ship. This is not a merchant ship, this is a naval ship, for example. If assume that there is a V-shaped naval ship. So then the phenomena is going to be different. The center of it is not going to be the center of rotation for a naval ship, but for a merchant ship, yes. But to achieve this, there should be few conditions needs to be there should be few the shape of the ship should be in a certain condition. That means both sides, if you look at the sides, they should be parallel. That is the only case where these two wedges are going to be equal. But we don't call it parallel, instead we call wall-sided. This is why it is called wall-sided. So it's like two walls in the side. If it is, that is why the wall-sided formula came in, right? Because these two wedges to be equal, you can see in a V-shaped ship it is not happening, but in this ship it is happening. That is why even in a container ship, the streamliner, the forward part is streamlined, aft part is streamlined, but midship section is parallel to each other, right? There is a wall-sided section in even in a container ship, right? In commercial ships. So the center of rotation, the pivot point is getting preserved here, right? So let's put this the same scenario into the longitudinal ship, longitudinal side. So this is about rolling, right? This is where the ship is getting rolled, right? And this is the point where the ship is getting rolled for a wall-sided ship, but not for a naval ship or V-sided or any other ship, right? But if you look at, put this same scenario, put this same method to the longitudinal direction as well, where the ship is pitching. Around what point the ship is pitching, right? So here the ship is pitching. All of you know that the point is called LCF, longitudinal center of rotation. That is why we do all the calculations based on LCF. Why the ship is getting pitching around this point, right? Where the ship is designed in such a way that this wedge is equal to this wedge. And so that totally depends on the ship shape, ship hull, right? So ship is designed in such a way to keep the LCF very close to midship. If you look at the hull, if you go to hydrostatic table, have a look where the LCF is, right? LCF is very close to midship area. Why? If assume that the LCF is somewhere here, based on the ship shape, I will draw a hypothetical ship, something like this, right? Something like this, where the aft part is more larger and bigger, and the forward part is smaller, where LCF will be somewhere here, right? So because this is a geometrical center of the water plane, right? LCF will be more towards aft. So when the trim is changing in this ship compared to the normal ship, when the trim is changing, let's say trim is changing by 1 meter, that means forward draft minus aft draft is 1 meter. When this is changing by 10 centimeter, this is changing by 90 centimeters. So for a commercial ship, this is not good because the pivoting, the pitching is more forward and pivoting is very less aft. So the pitching motion is more, and also for the calculation, it is very difficult. For example, if you have a container here and if you have a container here, if you want to do a trim calculation here, it is going to be extremely difficult in this case, right? For a bulk carrier, it is said for all the commercial ships, but when it comes to naval ships and other type of ships, that is not a big issue, right? So now you can see LCF for a commercial ship is by the ship shape, by the design itself, is kept in the middle, right? Hull shape is designed in such a way so that the LCF is the longitudinal, the geometrical center of the waterplane area between the load ship and the light ship. This is load ship and this is light ship. Between these two graphs, if you look at very closely in the hydrostatic table, the hull is designed in such a way that the LCF is very close to midship, where the aft draft change and the forward draft change is almost equal to each other. But there is a slight difference, but almost, let's say this is changed by 50 centimeters, this is also changing by 50 centimeters very closely, okay? Not exactly, because still the LCF is not exactly in the midship. It could move here and there, maybe 3 meters, 4 meters, but not definitely 10 meters. It is not going to be more than 5-6 meters for a big bulk carrier, right? So it should be somewhere in the middle, in midship area, right? So now this is where the ship is pivoting. Even during Scott, this is the point where the ship is going to pivot. So that means trim is changing from this point only. Even during a loading condition, even during trimming condition, this is where the ship is going to pivot. Even in the dry docking condition, this is where the ship is going to pivot, right? LCF. But during Scott also, it is going to be the same. Now, during Scott, what will happen is that I'm going to draw 2 types of ships. One is a bulk carrier, other one is a container ship. If you look at a container ship, under the keel, if you look at the keel in a container, I'm not talking about the hull, I'm talking about the keel here. If you look at the keel is more streamlined to the forward, but bulging in the aft. In a container, this is a streamlined vessel or a container ship, for example. But if you take a bulk carrier or a tanker, more bulging towards forward and aft is streamlined. Next time when you visit a ship or when you go to the ship, you can have a look about this phenomena that this is a bulk carrier. This is basically branch ships. We call it branch ships. Okay, bulk carrier, for example, let's say a tanker. So in the streamliner, like this is the keel, okay, not the waterplane area. This is the keel I'm talking about. So waterplane area is above this, right? Now in a container ship, now you can see it is more area in the keel towards aft from the midship. But in a bulk carrier and a container, or the block coefficient, if it is more than 0.7 are branch ships, and less than 0.7 is considered as streamliners, block coefficient CB. Okay, so here you can see the underwater keel area, right? It is more area towards aft in a container or streamline, but it is more area in the bulk carrier towards forward. So now you think from the pressure drop. So pressure is dropping because of the water flow, right? You saw that in previous explanation. But if you look very closely, the resultant of all the pressure drops in the keel, resultant is lying in this ship more towards forward. Resultant of pressure drop is more towards forward, but in this ship, it is more towards aft. That is the reason when it is more towards aft, because of Scott, this ship going to trim by aft. Trim by aft. But this ship, because the resultant is much more towards the forward, this ship is going to trim by forward. So that means if I go in this direction, if this is a container ship, it is going to trim like this because of Scott. But if it is a bulk carrier or a tanker, it is going to be down by head. It is going to be down by head. So this is why that the blunt ships or the bulk carriers or tankers are going to trim by head during Scott, but the streamliners are going to trim by stern during Scott. So let me hand over back to Captain Harindra Perera for the question and answers.
Thank you, Captain Dhakshina. We have another question from Keshwa Linage. He's asking if a master identifies when a pilot is doing a maneuver and the maneuver is questionable, and that decision the pilot has taken will affect the vessel's steering and the squat. What advice would you give the master to handle such a situation so that the vessel still can berth in a timely manner and there will be no arguments between the pilot and the master on the bridge? Like there is some technical difficulties. We'll go back to Captain Dhakshina. He will continue the lecture.
Right. Until Captain Hagen comes in, let me continue this one. Hope you can, all of you can hear me, right? You can hear me, right? Okay. So let me continue this furthermore. Now, there is a question from Lieutenant Ahmed, that when a naval ship or V-shaped hull ships navigate in canal or narrow channel, should we consider the blockage factor for Scott, or does the blockage factor affect the Scott massively, and how? Okay, I will. My next explanation is about the formulas that how the Scott is being how to determine the Scott. What is, you have to quantify it. So when I'm explaining about the formulas, we'll explain, we'll give the answer for this question, the blockage factor, right? So I'm going to share my screen where you all can see the formulas up to now, right? Some few formulas. Where the Scott to determine the Scott, people have done several researches, and there are so many formulas. You can see different people have given different formulas for Scott, right? And nobody up to now has given, nobody have done a research, and nobody up to now have given a specific formula to find the Scott, the amount of Scott. So there are several constraints in this finding, and still it is an unknown factor up to now. Not unknown, it is known, but not so calculable factor. Scott is not that calculable up to now. So nobody have given a perfect formula to find the Scott. But you can see here, there are several formulas. I can, maybe you can see the screen where it says ICO, RELS, several formula, then Yoshimura formula, then Guliev and Huska formula, then Ramesh formula, Hooft formula, then Milward formula. But the very famous one is the Barras formula, because it's simple compared to the other formulas. That is why, right? It's quite simple, this formula. You can see, right? This CB is the block coefficient of the ship, and S is the blockage factor. I will explain what the blockage factor is. This is the blockage factor, S. I'm talking about the Barras formula. I'm not talking about the other formulas because they are pretty much highly technical formulas, but this is the simple formula that as mariners we can use, right? But you can see even still it is a bit complicated, where the power to the S is, the blockage factor power to the S is 2 divided by 3, or in decimal places it is 0.81, and the velocity into 2.08, the power of 2.08, right? So even this one, have been simplified. Now the answer for the Lieutenant Ahmed question is yes, the blockage factor is getting affected here, right? So the blockage factor, let me explain the blockage factor. Right, hope you all can see my screen. The blockage factor, let's say there are different type of waters. Now you have deep water, you have confined waters, and you have open shallow waters. Now deep water everybody knows, but let me go open shallow waters. That means you have a ship and this is shallow water, but the boundaries on the sides are far away, right? So this is shallow water. So this is open shallow water. But when it comes to confined waters, that means both the undergate clearance is also restricted, and the side of the ship is also restricted. So this is confined waters. So in confined waters, the blockage factor, right, is the area of the cross section of the ship, if I put it as simply, to the area of the cross section of the channel. Right, this is the blockage factor. So if you take S, the area, so A divided by capital A. So capital A is the area of the confined water. So this is getting affected to Scott Y. You can see in the previous formula, I will write the formula here. Scott is equals to CB divided by 30 into S into the power V into 2.08. So here you can see the blockage factor is a direct variable for Scott, right? But there are certain constraints in this formula, right? You cannot use this formula for all the situations. There are certain constraints, but I will not go into that detail, right? There is a comparison of the formula, and every formula is having constraint. That means you cannot use this formula for all the situations, right? There are certain constraints, right? So the blockage factor for a naval ship or a V-shaped ship, yes. So the hull ship shape, depending on the hull, how the Scott is affecting will be varying. For example, as I explained earlier, in a commercial ship, it is flat bottom most of the time, right? Where huge amount of Scott effect will be there because the relative water movement is very high underneath this hull, right? But when it comes to a naval ship, if you look at this one, right, a V-shaped ship, where the relative water movement is comparatively to this flat bottom, right, comparatively less. So the Scott, by theoretically we can say that the Scott in a naval ship is going to be less than compared to a commercial vessel. You can see that it is obvious that from these two diagrams that this is going to be less than this one, because underwater, if you look at the keel shape, it is flat bottom in a commercial ship and it is a V shape in a naval vessel, right? So blockage factor, yes, it is a direct variable to Scott, and depending on the ship's hull, the amount of the Scott will be varying, but Scott will be there, right? So shall I hand over to I will hand over to Captain Harin. Okay, let me continue a little bit furthermore, right? So let me simplify this formula. Let me simplify. I have not simplified. It's actually Dr. Barras has simplified this one, right? So let me show a simplified formula where we can easily calculate this up to a certain approximation. It is not exactly the amount of Scott, but approximation can be taken, right? Because we cannot find out the blockage factor when we are on board a ship. It is not possible to find a blockage factor. So we have to get some assumptions. We have to go through some assumptions and give a certain constant to this factor S, right? Then only we can approximate So then we can simplify the Barras formula for Scott up to a certain level. Yoshan, shall we go to the third slide?
We have a question for Captain Harindra.
Yeah, okay.
So the question is, we just got the question just now from another seafarer. His name is Bhaskar. He has asked, suppose that you need to berth a vessel during a time where the wind is over 20 knots and the ship's UKC is at a minimum due to the swell, and the UKC value is unpredictable because of the prevailing swell. What extra precaution will you take as a master and as a pilot?
Yes, thank you, Yoshan, for that. Can you hear me? Yeah. Thank you, Yoshan, for that question. Especially if you are unsure of your UKC and swell conditions and weather conditions, and what we normally do is before getting into the channel, we would like to in the open sea, if you board the ship early, and if it's a tidal vessel, to be on high water slack, to be at the berth, we will try to do the same heading before we enter the channel with a beam swell, and at that speed, how much the ship is going to roll. And then we'll calculate what sort of UKC is necessary. If you are unsure of the swell conditions, we will do that in the open sea and see the how much is going to roll, and then calculate accordingly. And that will be the way forward to proceed in that channel, open sea channel, which is not protected by the swell and waves. So that would be the way to do it. So I would like to also tell another, it was a real catch-22 situation where the Ever Given was concerned blocking the Suez Canal, because I was speaking to one of the masters on the sister vessel. And when the pilots boarded, the master, due to commercial pressure, was very happy that the two pilots agreed to take the ship in that kind of wind condition. But we are talking about bank effect and all the other effects as well, connected UKC, Scott, interaction, all are interconnected. So the ship had to proceed. If she had this kind of wind, she was going to, the slower she went, she was going to drift onto the bank. So she had to be, the speed had to be increased. And as you know, the Suez Canal, they are doing around 9 knots. But in this case, when she ran aground or when she hit the bank, it was around 13.5 knots. So they had to increase the speed. So it was a catch, and you couldn't reduce the speed to reduce the Scott and the interaction, because you were going to set onto the bank due to the wind condition. And when you increase the speed, the interaction effects were much greater. And she, there was a problem with the steering as well. And as I told you earlier, in the steering, and she hit the bank. So after that only we were talking about the trim conditions. And later on, the company had also said in very vulnerable ships, instead of being even keel, it might be better for the ship to be trimmed by the stern, maybe 1 meter or so, because in case you go across the bank and the bulbous bow area touches the bank, it is much easier to refloat the vessel by having a stern trim. Yes, so that was also mentioned by this master of the Evergoods who was speaking to me. And so it was a very difficult situation for the pilots as well as the master in that kind of situation to maintain to reduce the drift due to the wind, and you had to increase speed. So, so it was a real catch-22 situation. Thank you.
Thank you, Captain Harindra, for the valuable insight for that question. We will go back to Captain Dhakshina for the remaining of the presentation.
Yeah, thank you, Yashan. Can you transfer me the screen, please? Yeah. You can hear me, right? Yeah. Okay, so now, again, let me refresh. Scott is equals to, according to the Barras formula, okay, there are, as I showed you, there are several formulas. The Scott is equals to the block coefficient. So these are the variables there in this formula: block coefficient, blockage factor, ship's velocity. Right. So there is a question somebody have asked, that does the weather affects the formula? Or when the passage plan is getting, I mean, when you're doing the passage plan, can the weather can be considered in this formula? No, it is not possible. You can see, look at the variables in the formula. For example, you know the block coefficient of the ship, right? So block coefficient has nothing to do with the weather condition. Then the blockage factor. In a confined water, the cross section of the ship compared to the cross section of the channel. So blockage factor also cannot be considered in the weather condition. Whether the weather condition, it's not possible to find the blockage factor, how much it is exactly. Then the velocity of the ship. So that is also, again, what the ship is, even in whatever the weather condition, ship is going to settle down in a certain velocity. So that velocity will be directly taken into calculation of this, right? So the weather condition will not be basically affected to the formula, and you cannot even use the weather condition inside this formula, because there is no any variable for the weather condition. Right. So let me simplify the formula a little bit furthermore. Yashan, can you put the slide, please? Third slide. Okay. So until the Yashan comes in with the slide, I will show you the formula itself. Right. Now Dr. Barras have simplified this formula for two situations. Right. One is for confined waters. Okay, and the other one is for deep waters. You can see the slides here, right? Go to the other slide. Okay, here you can see. So there are two scenarios that the simplification of this formula have been done, where for the open waters and for the confined waters, right? So for the open waters, that means open shallow waters, the block coefficient, right, into the speed through the water square divided by 100. But for the confined waters, block coefficient into the speed through water divided by 50. Yushan, can you give me the screen back? Can you give me the screen back? Yes. Okay. So you can see for the confined waters, right, the Scott is equals to block coefficient divided by 50 into V squared, right? But in open waters, Scott is equals to block coefficient divided by 100. So this is a simplified version where the blockage factor have not been considered. Right there. It's not that actually it is considered. You can see that this 30 have become 50 and 100. So that means a certain constant, the blockage factor have been assumed. Assumption have been taken for the blockage factor with a certain constant. That is why this have been derived simplified by taking out the blockage factor, because on board a ship it is very difficult to find out the blockage factor as a navigator, right? So you can see there are two differences. This is divided by 50 and this is divided by 100. So you can see the Scott value here is more compared to the Scott value here. As Captain Harindra explained, in confined waters or in shallow waters, the blockage factor, the Scott is increasing, right, compared to the open waters. In confined waters, the Scott is increasing compared to the open waters. That is why you can see it is divided by 50 here and it is divided by 100. So this is a very simple formula, but with certain restraints. You cannot use this in all conditions. With the certain restraints, this formula can be used. So those restraints have something to do with the depth of the water and the velocity of the water, velocity of the ship. So there are within the certain restrictions only these two formulas can be used. I hope that I hope that I have I tried my level best to explain the Scott and all the formulas hydrodynamics within the short period of time, right? So furthermore, if you have further questions, please drop in here. I would like to hand over it to
Captain, there's one question that was addressed for you.
Yeah. Okay.
They're asking when a naval ship or V-shaped hull ships navigate in the canal.
Yoshan, that one I already explained.
You already explained that. All right. Yeah. So then with that, we will proceed to Captain Harindra. Sir, Captain, there is a question for you. A vessel is going to the berth in a narrow channel or river with considerable current against, or the current can be favorable. How would the current affect the squad, and does the current affect the squad actually?
Yes, thank you for that question. And the effect of the current. Sometimes you have to proceed to berth at high water slack with the current behind, or we have to berth at low water slack with the current ahead, that is on the flood or the ebb. So that affects the current, because sometimes the current effects are there because you have to increase the speed to have good steering. Otherwise, your steering is very, very poor. So that affects, and there will be increased cost. Now, the most danger is that in case of Scott, what you do is you will not, it's not like running aground. It is that you will be touching bottom, and then you might still continue to proceed. And that is the danger, where you would have damaged your bottom area, and still you are unaware that you had touched bottom, and you will still continue to proceed in the channel. And this is the standard problem we have, is that if you go to, if you see your maneuvering diagram or maneuvering booklet for that matter, the Scott tables are usually given for 1.5 times the draft or twice the draft. So that is on a 10-meter ship, you will have 5 meters under keel clearance. But if you have to go with 1 meter, most ports allow you to go with 1 meter UKC. There is nothing for us to plan our passage, and the Scott tables are so completely way out, because the Scott tables are given for 1.5 times the draft or twice the draft. So there will be, so it is say 1 meter is UKC is the Scott is going to be so much higher, and you are going to, when you go astern or when you go to cant or your stopping distances, all that affects your maneuverability. Yes. So I hope that answer is clear to you.
Thank you, Captain, for your answer. And I would like to thank everyone who attended this webinar today. And also I would like to specially thank the two keynote speakers today, Captain Dhakshina Perera and Captain Harindra Perera, for taking a small amount of time from their very busy schedule and to part with us with some very valuable information, which I think will be very helpful for our Sri Lankan seafarers. Thank you so much, sir. Thank you so much, sir, for spending your time here. And if you have any other questions for them, please send it to us in the Nautical Institute page and we can address it to them directly. I would like to thank everyone who is here. Special thanks to Mr. Telvatta for organizing this event today. And my name is Yoshan Perera. I was the moderator.